Suppose we are counting the number of occurrences of an event in a given unit of time or distance or area or volume. For example, we might be counting out the number of customers in a day in a shop like pen shop, perhaps, or the number of dandelions in a square meter plot of land. Then the number of events is going to be a random variable that may or may not have the Poisson distribution, depending on the specifics of the situation. But the Poisson random variable is a count of the number of occurrences of an event.
I'm going to phrase the following terms of time with the same ideas hold if we're discussing distance or area or volume, etc. Suppose events are occurring independently. In other words, knowing when one event happens gives absolutely no information about when another event will occur, and the probability that an event occurs in a given length of time doesn't change. Through time, in other words, the theoretical rate at which the events are occurring does not change through time. A little more loosely, we might say that the events are occurring randomly and independently.
If these conditions totally hold, then the random variable x, which represents the number of events in a fixed unit of time, has the Poisson distribution. Here's the probability mass function for the Poisson distribution. What we'll use to calculate probabilities is the probability the random variable x takes on the value little x, which you'll sometimes see written as p of little x as equal to lambda to the x times e to the minus lambda over x factorial. E, like pi, is an important mathematical constant in the base of natural logarithm. It is approximately 2.71828, but it is a rational number that has an infinite non-repeating decimal places. We've discussed factorials previously, but as a specific example of this x factorial, 5 factorial would be 5 times, 4 times, 3 times, and 2 times 1, and that would be 120. It's not a probability distribution until we say what values x can take on. Here, the random variable is a count of the number of events in a given unit of time, and so it can take on any non-negative whole number value, so that this is the probability mass function that we use to calculate probabilities for any value of little x that's 0, 1, 2, up to infinity. There is no upper bound on the value that x can take on, but depending on the situation, probabilities eventually get tiny for large values of x. The mean of the Poisson distribution is lambda, so mu, the mean of the random variable x, is equal to the lambda. So we could have used mu as our parameter, and some sources do that, but we often use lambda for the Poisson distribution. The variance of the Poisson distribution, which we'll label as sigma squared, is also equal to lambda. For the Poisson distribution, the mean and variance are equal.
Let's take a look at an example. In Paseo de Santiago, Iligan City, an average of 16 waves reach the shore in a minute. What is the probability that exactly 20 waves reach the shore in 1 minute? To solve for the probability, we use the formula p of x is equal to e raised to negative lambda times lambda raised to x over x factorial, where e is a constant number approximately equal to 2.71828, and lambda is equal to the mean of the distribution, which is 16, and x is equal to 20. If we substitute these values to the function, we get p of x is equal to e raised to negative 16 times 16 raised to 20 over 20 factorial, and we get approximately 0.0559. We get a really small value since we are using the Poisson distribution, and events occur randomly and independently. And if we take a look at the graph, it looks like this. The shape of the graph is bell-shaped because probabilities are evenly distributed throughout the graph. And even if we calculate for the probability of a value closer to the mean, we still get a value less than 10%. since events occur very randomly and we do not know the outcome. And that's how Poisson distribution works.